Expressions are something like this. For example, x squared plus x minus 6. This is an expression. It's a quadratic expression. Cartesian equations are like this. Y equals to x squared plus x minus 6. So this is the equation of a curve. When we differentiate an expression, we write it like this. The question would be differentiate, and we write d by dx of x squared plus x minus 6, and the derivative is twice x plus 1. But here we have both sides. So we already know what this is, but what is the derivative of y? D by dx of y is written as dy by dx. So d by dx of y on one side equals to d by dx of x squared plus x minus 6 on the other side. So therefore, d by dx of y, the derivative is dy by dx. Then we write the equal to sign, and the d by dx of x squared plus x minus 6 is twice x plus 1. So that way we can find dy by dx. So another example would be y equals to x cubed plus x squared plus x plus 1. Therefore, let me skip the second line over here. So d by dx of y is dy by dx. I have done the derivative on one side equals to the derivative on this side by the addition rule. I'm going to do the derivative and keep adding. So this is going to be x cubed, which is 3x squared, plus x squared is twice x, plus x is 1, and 1, the derivative is 0. So this is the derivative of a Cartesian equation. Now it is different from expression, because when we do derivative of an expression, we just write d by dx. We know that the rule for gradient is d change of y-axis, change of y divided by change of x. So this can be thought of as change is the symbol d stands for change, and this is dx. So dy by dx stands for the gradient of a Cartesian curve. Now the gradient of curves can be thought of as how does the slope of a mountain look. Now take a look here. The mountain is a very complicated structure. It has different slopes at different points. You cannot just say you're climbing smoothly. No, there is a crevices here, and then there is a turn here, so it looks a bit different at different points. So this is what a mountain looks like, and we can compare the slope of mountains, which is not constant, to the slope of curve. If you come closer here, you will see that how it changes here, and that's what happens. So in case of a curve, we don't have a fixed gradient. At different points we have different gradients, and we can find this complicated gradient using calculus, which is differential calculus. When we differentiate, we can find the change of y with change of x for a very small amount, because you see, it doesn't matter what type of a mountain it is, if you consider it for a very small portion. If I zoom in and look at a very small portion here over here, it will look like a line for a very, very small portion. So that's what we are doing. We are trying to find a point for which the gradient of the curve is fixed, and that's how we find the gradient of the curve. But throughout it is not constant. It is changing, and it is changing from different points. Now on the other hand, gradient of lines are fixed. So we can think of them as stairs. Just like stairs have fixed gradients, we can think of them as fixed gradients. So for this particular line, we see that the stairs is fixed. It's climbing in a certain way. So the slope of the line is the same as the slope of the stairs. It is fixed. So we need a point to find the gradient of a curve. If you know the point, then we can find a gradient for a curve for that particular point, because there is no such thing as gradient of the entire curve, because the curve keeps changing direction. So when I say gradient of the curve, I mean what is the gradient of the curve at a particular point. For this particular point, it has one gradient. Suppose this is dy by dx. At another point, it would have another gradient, another dy by dx value. at another point it would have another gradient, another value for dy by dx. For everything we need to know here, we need a point. A point is an ordered pair. Bracket open, x value, comma, x value, bracket close. So this is how it works. Let's start with some examples. Now here we have an expression function fx. But remember, they have mentioned that y equals to fx. So that simply means all we have to do is we have to think of this as a shortcut for y. So saving space. So when we write here question number A, so y is really x into x plus 1. So we know we have to simplify this before we can differentiate this. X into x is x squared, x into 1 is x. So let's find the gradient. We have to find the gradient of the curve. Gradient is dy by dx. So the derivative of y is dy by dx equals to the derivative of x squared is twice x plus 1. Now we found an expression for gradient. We need to find the gradient at the point A. At the point A, we have the value of x 0 and the value of y 0. So the value of x is only needed for finding the gradient. Let's plug in the value of x here. So we get 2 into 0 plus 1 equals to 1. So the gradient is 1. So remember, we found the gradient of the curve at the point A. At another point, the gradient of the same curve would be different. Now let me say something about when we differentiate y, the derivative is written as dy by dx. What about differentiating fx? After all, they are writing y equals to fx. The derivative of fx is written as f prime x. Now be very careful. This is f a little minus 1x. This is called the inverse of the function. But when we write f with a little dash over here, we call it the derivative or the first derivative of fx. So it is very important to remember f prime x and f inverse x are very, very different. F prime x on the other hand is the same as dy by dx. They are the same. So if we do another example, let me do number B over here. So that means this time let me write, instead of writing dy by dx, let me simplify fx. It's the same thing, makes no difference. So we can write 2x divided by x squared to simplify the expression. We can write 2. So x to the power 1 minus 2. This is the indices rule. You subtract the power and we bring the value of x squared upstairs. So we write 2 x to the power minus 1 minus 6x to the power minus 2. So the derivative or the gradient f prime x d by dx of fx is f prime x. So 2, this will be minus x to the power minus 2 minus 6, this will be minus 2 x to the power minus 3. Minus 2 minus 1 is minus 3. Let me write this down as positive power. So this becomes x squared. Minus 6 into minus 2 becomes 12. This becomes x cubed. So therefore, now we have to find the gradient at the point A again. So at A, this time the x coordinate is 3. So x equals to 3. So let's find the gradient. So f prime 3, just the different notation, is the same as dy by dx. Minus 2 divided by 3 squared plus 12 divided by 3 cubed. So this would be minus 2 by 9 plus this would be 12 by 27. So this turns out to be 2 by 9. So the gradient of the curve is 2 by 9. So this is the same way of doing the sum. Now if I did the sum by writing dy by dx instead of fx, let me now remove this. So instead of fx, so I would be writing y. Instead of f prime x, I would be writing dy by dx. Instead of f prime 3 here, so we are going to write dy by dx. So see, there is not much of a difference by doing a sum in terms of a function or doing in terms of dy by dx. Now let's do one more sum. Let me do number D. So number D is, let me use y since y equals to fx. So y equals to 3x minus 4. So this is x squared downstairs, and we bring it upstairs to the power minus 2. We have to find the gradient of the curve at the point 2, 5. So dy by dx, so the derivative of y is dy by dx. So this would be 3. Let me do this directly. Minus 4 into minus 2 is plus 8. X to the power minus 3. So this would be 3 plus 8 by x cubed. So at the point A, the x coordinate is 2. So at A, x equals to 2. So we can write dy by dx equals to 3 plus 8 by 2 cubed. So 3 plus 8 by 8, which is 3 plus 1. So the gradient of the curve at the point A is 4.